Hey everyone, and welcome to this explainer. If you're prepping for your Cambridge additional mathematics exams, you already know that kinematics can sometimes feel like this messy collision of abstract physics and heavy algebra. But honestly, it really doesn't have to be. Today, we're going to transform complex kinematics into a strategic, step-by-step blueprint for mastering those 0606 math exams. We're going to completely strip away the confusion and just focus exactly on what you need to extract those top marks. So let's just dive right into it.
To get our minds in gear, I want you to picture this. Consider a spacecraft leaving Earth, heading on a journey directly towards Jupiter. Its initial direction is aimed perfectly at the gas giant, but does it actually travel in a perfectly straight line? Well, as Maria Mitchell so beautifully put it, we shouldn't just look at stars as bright spots. We need to take in the vastness of the universe. To make sense of all this vastness in kinematics, we kind of have to simplify things. We model complex objects as single particles moving in straight lines. But to do that accurately, we absolutely must define our parameters clearly, things like starting points and positive directions.
So here is our game plan for today. We've got 4 distinct parts. First, defining the core variables. Second, the calculus blueprint. Third, mastering motion graphs. And finally, exam strategy in action. All right, part 1, defining the core variables. You know, it's actually amazing how often these two basic terms get mixed up on exam papers. You've got to be super careful not to confuse speed, which only has size or magnitude, with velocity, which includes both magnitude and a very specific direction. Think of it like this. If we take upwards as positive, a speed of 3 meters per second upwards is a velocity of positive 3. But a speed of 3 meters per second downwards, that's a velocity of negative 3. Basically, velocity cares about your direction, and speed, well, speed just doesn't. And similarly, we've got a really vital distinction between distance and displacement. Distance simply measures the total path, like literally how far you physically traveled. If you walk 5 meters forward and then 5 meters straight back, your distance is 10 meters. But displacement, that measures exactly where you are relative to your starting fixed origin. So in that exact same scenario, your displacement would be a big fat 0. In kinematics, we are primarily working with displacement, so we can precisely track position over time.
Okay, I want you to take a quick mental screenshot of this data table right here. These standard SI units and notations are literally the essential vocabulary of every single kinematics question you're going to face. Notice how displacement is usually represented by S, velocity by V, and acceleration by A. But more importantly, look closely at the notations involving d over dt, like ds over dt or dv over dt. This right here is our bridge into the math. Understanding this specific notation is absolutely crucial because it unlocks the entire calculus approach to kinematics that we're about to jump into.
Which brings us nicely to part 2, the calculus blueprint. So when acceleration is varying with time, you simply have to use calculus. Think of differentiation as your forward gear. Let's build some forward momentum, right? If you have an expression for displacement, differentiating it with respect to time gives you your velocity. And if you differentiate that velocity, you get acceleration. It's a very direct sequential chain, S to V to A. You just keep moving forward. Now on the flip side, integration is your reverse gear. If you're given acceleration, you integrate it to find velocity. Integrate velocity, and boom, you find displacement. But, and this is a massive trap where so many students lose easy marks, you absolutely must always include the constants of integration, usually C and K. Think about what this actually means in the exam room. These aren't just annoying mathematical formalities. They represent real physical states, like your initial velocity and your starting position. So please, always use your initial conditions to solve for them. All right, let's actually test this blueprint with a real-world problem. From our source material, we need to determine if a sports car, which has this exact displacement formula, is breaking the British speed limit of 70 miles per hour after exactly 4 seconds. So how on earth do we figure that out? Well, we need to find its speed at that exact, precise moment. And this just brilliantly illustrates the sheer power of our calculus blueprint. By differentiating that displacement formula to find the velocity equation, and then just plugging in those 4 seconds, we get 48 meters per second. When you convert that over to miles per hour, it translates to a massive 108 miles per hour. So yeah, the driver is definitely absolutely breaking the limit. You see? You didn't need to place radar gun for that. You literally just needed the first derivative. Moving right along to part 3, mastering motion graphs. Visualizing motion through graphs is another completely critical skill, so you need to lock these rules into your memory. The gradient or the steepness of a graph always represents a rate of change.
So, the gradient of a displacement time graph is velocity, and the gradient of a velocity time graph is your acceleration. But hey, remember our reverse gear, integration? Visually speaking, integration finds the area under a curve. Therefore, the area under a velocity time graph gives you the total displacement. Just let that sink in for a second, because it's a real game changer.
And finally, part 4, exam strategy in action. Honestly, the hardest part of the exam usually isn't the calculus itself. It's translating the examiner's tricky English phrasing into actionable mathematical triggers. When you're reading a question, you should be aggressively scanning for these specific phrases. Listen closely. When you see instantaneous rest, you should instantly know to set your velocity equation to 0. If the paper says velocity stops increasing, that means the rate of change of velocity has flatlined, so you set acceleration to 0. Initial always means time equals 0. And here's a classic examiner trick. Distance in the third second. That means you need to perfectly integrate between time equals 2 and time equals 3, not 0 to 3. Keep these triggers fresh in your mind, and you'll be golden. Let's actually apply this blueprint to a real June 2013 Cambridge question. Okay, so we're given the velocity, we scan and see our trigger phrase, instantaneous rest. Step 1, we set the velocity equation to 0 and solve for t to find out exactly when the particle stops. Step 2, well, we need distance, right? So we use our reverse gear. We integrate the velocity equation to get our displacement equation. Step 3, we plug the time we found in step 1 directly into our brand new displacement equation. It's just a perfectly logical, structured process. Step by step, it builds right to the correct answer. So, armed with these forward and reverse calculus gears, your solid knowledge of graph gradients and areas, and your brand new ability to decode that sneaky exam phrasing, you have everything you need. You aren't just memorizing formulas anymore. You are literally modeling the universe, one particle at a time. So, how are you going to approach your next past paper? Are you going to let the algebra overwhelm you, or will you apply this strategic blueprint? The choice is entirely yours. Stop memorizing, start modeling, and I will see you in the next explainer.